Hello students, let's go to section 3, Laplace transform methods. In this section, we are going to focus upon this kind of equations. Homogeneous linear ODEs with variable coefficients, where the coefficient functions are linear polynomials of t, bt plus c form. Here are some examples. Please pay attention to the coefficient functions. They are either degree 1 or degree 0. When b is equal to 0, then this part just drops out. Then we have just constant, like these. Otherwise, we have some t terms, but no t squared or t cubed or anything like that. Nothing transcendental, of course. In that kind of problems, we're going to use this formula here, blue formula here, as our main tool. We call it output derivative formula. Let's begin from here. Y of t, the small y of t is the input function, and capital Y of s is the output function under the Laplace transformation. And as a matter of fact, I need of s here as well, but there are too many characters, so let's abbreviate it away. But still, in any case, the Laplace transform is a function of s. Now, what does this formula tell us? The derivative of the output function, the Laplace transform, turns out to be the Laplace transform of negative t times y of t. That's what this theorem is talking about. And of course, this negative sign, I can always bring it out. Equivalently speaking, we get something like this. The ds of y of s is equivalent to the Laplace transform of negative t times y of t, like this. So taking the derivative of the output function is equivalent to multiplying negative t to the input function. That's what this formula is talking about, to tell the truth. And you can always take this negative out. So we have t and y of t. You're going to get something like this. So the derivative gives rise to multiplying t and also negative sign like this. That's what this second formula here, blue formula, is talking about. Now, what if I take the derivative once again? Let's go back to this expression here. All right. So taking the derivative of the output is the same as multiplying by negative t to the input. Now, what if I take the derivative once again? I'm doing this once again, which means multiplying by negative t yet again. So we have negative t squared, which will of course become positive. And then take another derivative. That's going to be multiplying negative t 3 times, and so on and so forth. In general, you're going to get this kind of expression. Now look at the green formula here. This is also kind of in line. You take the integral, and integral is basically the antiderivative. So instead of multiplying by negative t, we divide. So we have 1 over t. But why 1 over t? Why not 1 over negative t? Well, that's because s is downstairs here. S to infinity instead of s on top. If s had been on top, then we will have this negative, same as before, but the switching changed the sign. It's coming from the fundamental theorem of calculus, of course. Now let's look at the proof, and the proof is actually surprisingly simple. Let's begin from this, the basic definition of the Laplace transform, and then we take the derivative by s. Now this y of t dt, everything here is all about t, and the only s expression is this one here, this exponential. So we simply take the derivative to this guy only, and what is the derivative of the exponential function? Exponential always stays the same, and by the chain rule, we have to multiply the derivative of the inside, and that's negative t. This comes from the chain rule. Now let's compare this expression, the final expression, with the original. Instead of y of t, we have negative ty of t. That's the only difference. So this final expression tells me that this is a Laplace transform of negative t dt, negative ty of t, excuse me. And then, of course, I can take negative outside, like this. So that's a whole proof. It's not too difficult. How about the second one? Well, this is going to be a little bit harder, but still, it's not too bad at all. So we have this, the Laplace transform, and let's take the integral. Now, we're taking the integral to s to infinity and sigma, because sigma is a Greek letter that corresponds to s. So we're switching s to sigma and then putting s here, s to infinity. Now, the other part here, y of t dt, all these are about t's only, nothing about s or sigma. So this integral applies only to the exponential here. So we have this exponential, and the integral of exponential negative sigma t d sigma, like this. And then from here, we can apply the fundamental theorem of calculus. So we have the antiderivative here, and plug in the top and plug in the bottom, subtransform from the other. Plug in the top, what do you get? E to the negative infinity, and that's 0. And plug in the bottom and subtract, then we have minus, minus, plus. In the end, what do we have? We have 1 over t and y of t over here, and the exponential. So compare this final expression with the original. What's the difference? Instead of y, we get 1 over ty. So this is the Laplace transform of 1 over ty. That's a proof of the second problem here. But the second formula is not important for our purpose. This is the important one. Let's copy and paste that thing, and let's move it down here so that we can use it in example problems. Before moving on, how about these generalized formulas for second derivatives and higher derivative? No big deal, actually. We simply take the second derivative, exponential always stay the same, and repeat the chain rule, multiply by negative t each time you take the derivative. So negative t to the k power in general. Okay, alright. Here's a formula that we are going to be using, or let me copy and paste that thing back again here, down here. And then let's use it to solve a homogeneous linear ODE of this form, the target form, where the coefficient function is linear polynomial or less. Here's a nice problem, so let's begin with this one. Okay, and we're going to be using this output derivative formula. Okay, here we go. Ty double prime minus 1 plus Ty prime plus y equal to 0. Now, this is about Laplace transform method, so I have to take the Laplace transform, but before that, I have to break up this parenthesis. I'll tell you why in a moment. Did I break up okay? I guess so. Now, why did I break up? Look at this formula here. I have t times y, not 1 plus t times y, or 3 minus t times y, or anything like that. I need t times that. That's why I broke up, so that I have t times something, t times something. Okay, alright. I broke up, so let's take a Laplace transform. Ty double prime minus the Laplace transform of y prime minus the Laplace transform of ty prime plus, sorry about that, wrong key, okay, alright. did I get everything here? The Laplace transform is linear, so I can break all these up, and then we have the right-hand side there. The Laplace transform of 0 is 0, and the Laplace transform of y is capital Y, no problem there. This one, the Laplace transform of y prime, I hope everybody remembers, is the input derivative formula, and this is something we have been using all the time, going all the way back to chapter 2. If you're unsure, you can always go back to the page 123, the Laplace table. These two are problem. Those two are problems. And let's apply the output derivative formula to take care of those. So how do we handle it? I'm going to remove this t. In the end, instead, that becomes a derivative. And don't forget the negative sign, this negative. So this y, capital Y, is without this t. And I'm applying the same thing to not y, but y double prime, basically. So that and that replace this multiplication by t. Same here, same, okay, we did the same thing there. Remove this t. And derivative, and don't forget this sign change here. And this sign change here and this derivative replace this multiplication by t. That's how I applied this output derivative formula. The others are the same. Okay, let's do further computation here. Easy things first. The Laplace transform of 0 is of course 0. The Laplace transform of input function small y is capital Y. And how about this one? Something we had been doing all the time. Output derivative rule. Input derivative rule, excuse me. I hope everybody remembers this. And then of course we have the same thing here. Sy minus y0, and we're going to take the derivative a bit later. How about this one, y double prime? So that's s squared y minus s y0 minus y1. That's it, isn't it? And then I'm going to take the derivative a bit later. Okay, all right, we're there. And let's finish this computation. So, all right, and let's take the derivative of this s squared y. By product rule, we have 2sy plus s squared y prime. Are you with me here? Product rule. And then derivative of this, s just drops out, and the derivative of this part is constant, so it goes away. Looks like everything is done. I took all the derivatives, so I don't need this prime anymore. And that completes the first term. What do you think? Is everything okay? These two came from this, and this one came from this, and then this one went away. Same here, this one, okay, all right. The derivative of this, use the product rule, so y plus s y prime, and this is constant, so it's gone. So I don't need this prime anymore because I already took all those derivatives. And there you go, it's completed now. The Laplace transform method is now complete, and what's the resulting equation here? It's an equation of capital Y and capital Y prime. So the resulting equation is another differential equation. However, this equation is simpler than previous equation. This is second order. Now this is first order. Okay? This is a second order. This is first order. Here, we're taking a derivative when you have t times something, right? That's why we are taking only the linear polynomials as coefficient function. I don't want t squared or higher, because if I have t squared or higher, then I'm going to get capital Y double prime, or this derivative or higher, something transcendental, that of course is going to be kind of prohibitively difficult. With just linear polynomials, what we're going to end up here is going to be just first order linear ODE. Can you solve it? Can you solve any first order linear ODE? I'm very tempted to stop here and let you finish this, because we went through the solution method for the first order linear ODEs in week 2, the method of integrating factor. Maybe you can do it. Maybe you can stop this playback here and then try it on your own. Otherwise, okay, let me go ahead really quickly here. Okay, we went through this, broke up, all right, and we took the Laplace transform. We did all these. We are down here, and this is a first order linear ODE of capital Y. So how do you solve that? Somehow we'll have to express it in a standard form. Capital Y prime plus P of S times capital Y equals to F of S, that form. And then we get the integrating factor. Mu is e to the q power, where capital Q is the antiderivative of this part. So left-hand side, multiply integrating factor to both left-hand side and right-hand side. We get this kind of multiplication. And here in the left-hand side, we can consolidate everything into single derivative. So taking the antiderivative and then dividing away the integrating factor, there goes the solution. That's the method I'm going to use. I hope everybody remembers. If you don't, okay, here you go. The original equation. And simplify, take the like terms together, simplify, and then here's the standard form. Y prime plus py equals f form, all right? And then let's find the integrating factor. Capital Q is integration or antiderivative of P of S, but this one you can decompose by partial fraction. It can take some effort if you use paper and pencil method, but if you use computer algebra system, no big deal. Break it apart, and then we have log plus log. It's a good idea to consolidate them into single logarithm, and this is what we get. What's the integrating factor? E to the q power, so you have exponential of log, which cancel each other out. This is the integrating factor. S squared times s minus 1. You with me here? So this is basically what we are up to, the integrating factor, and we got up to here. Next, multiply integrating factor both left-hand side and right-hand side. It turns out left-hand side is consolidated into the single derivative of y times the integrating factor, and that's what this is, y times the integrating factor. And the right-hand side, f of s, which is already there, times the integrating factor. Turns out some simplification yields this. Next, take the antiderivative so that we get y times this. All right. This is the last antiderivative computation, so we need plus c. This one, we don't need it because we're going to get the antiderivative, the arbitrary constant later anyway. All right. Divide away by the integrating factor, we have a solution. We have the final solution of the first order linear ODE. It's the final solution of the first order linear ODE, but it's not the final solution of the problem, because what we want is small y of t. This is capital Y. Capital Y is the Laplace transform of small y, so we have to take Laplace inversion. How do I do that? For that purpose, I have to decompose it by partial fraction and then take the Laplace inversion, and here we go. Again, for decomposition by partial fraction, you can use computer algebra system. So y0 and the y0 plus c put together and another character b, so that we have two characters b and c, and as a matter of fact, we have two linearly independent solutions, e to the t power and t plus 1, and then we have these two characters. So we have the linear combination form. This is a general solution.